Hey guys, and welcome back to Chemistry 1032 instructional videos. I am your professor, Dr. Russell Betts, and I'll be guiding you through the final part of Chapter 4, Section 4.4, Nomenclature of Simple Alkenes. Nomenclature simply means naming for the most part. So let's just go through these little steps. The steps honestly aren't going to make a lot of sense until we see examples. Once we see examples, the steps will make a lot more sense, okay? So let's jot these steps down in your notes. Step 1, find the longest continuous, which means unbroken, chain of carbon atoms. This is the parent chain. Name the parent chain. So say you have an unbroken chain of carbons that has four carbons in a chain. You would call that a butane, right? If there was 5 unbroken, it'd be a pentane, 6 is hexane. That's the parent molecule. And everything else is named around that, okay? It'll make sense when we do it, I promise. All right, now, identify any branching points or any groups that are bonded to the main chain. For example, we could have something like this. H2, C, CH3, CH3, and then a hydrogen here or something like that. Well, this has got 1, 2, 3, 4 carbons, so it's a butane. But what about this methyl, this CH3 group called a methyl right here? We have to tell the reader what group that is and where to find it on the main chain. Again, these rules will make more sense once we start doing examples. That's as most things in life, right? They start to make a lot more sense when somebody applies the rules for you. Now, we have to remember that these groups that are attached to the main chain are known as substituents. Substituents is derived from the word substitute. Substitute means to replace with, okay? So what's happening when you have a substituent on an organic molecule, that group or that atom or groups of atoms are replacing a hydrogen, okay? So where a hydrogen should have been is substituted with this group. And if they are carbon-based or alkane-based, they are called alkyl groups. We're also going to see a little bit about halo groups, and those are group 17. Okay, so anything in group 17 that's attached to a organic molecule is called a halo group. So just write that down. We'll see when we get there. There's fluoro, chloro, iodo, bromo. Those are your group 17 elements. So we'll see alkyl and we'll see halo. All right? And I'll show you how to apply these rules. Don't worry. The rules don't make any sense. I know that. All right, number 3. Number the parent chain starting at the end nearer the substituent. Just write it down. Honestly, guys, it will make sense when we do examples. Step 4. Assign a number to each substituent based on location, listing the substituents in alphabetical order, not numerical order. It's always alphabetical at the beginning of the name. Separate numbers and words with dashes. Easy enough. Also, if there's more than one of the same substituents, you have to start using the prefixes di, tri, tetra. If there's only one, you don't. Okay? Again, what? I'm sure most of you are saying, what? And that's okay. Let's do an example. Oh, sorry, before we get there, here's just a few common substituents that you're going to run across. Here, this is called methyl. Now remember, methane, CH4, has 1 carbon. So a substituent with 1 carbon is called methyl. Okay? Now here's a substituent that has 2 carbons. Here's CH3, that's ethane. That becomes ethyl. So the ANE is replaced by YL when it's a substituent. Here's 3 carbons. 3 carbons is propane, so it becomes propyl. And so on. For the most part, the most common substituent you're going to see that's an alkyl group or a carbon-based group is methyl. Methyl is by far the more common substituent you'll see in this class. Okay? All right. Organic compounds with the same number of carbons can have the carbons connected in many different ways. Molecules that have the same molecular formula but a different connectivity, or in other words arrangement, those are called isomers. Now let's see an example of this. So that has a molecular formula C4H10. We could have drawn this molecule like this. Let me put it somewhere where I make sure you see it. This molecule also has the molecular formula C4H10. So these two molecules are related in that they're isomers of each other. They have the same chemical formula but different arrangement of the atoms. So the atoms have different chemical connectivity. I think all of you will agree that this molecule and this molecule are different. Okay, and they're known as isomers. So just make sure you know the definition for an exam. All right, structural isomers and conformational isomers. Cut that out. Let's do an example. Now, here we have, I'm going to redraw the molecule. I work better when I redraw molecules. I don't know why. There we go. And there's a bunch of hydrogens here. I guess I just like having more space on my molecule, so I can write things down and it's a little more clear. So I'm just drawing the same thing that's right over there on the left, just making it a little bit bigger. Now, rule number 1 was to find the longest continuous chain of carbons. So let's do that right now. 1, 2, 3, 4, 5. So this is a 5 carbon chain, so that's going to be pentane. Let's draw a little table right here, pentane. So whatever we call this thing is going to be this, that, and the other thing, pentane. So that's how we name it. It's going to be something, 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 pentane. Okay? Now the next rule said to find any substituents on the carbon chain. Well, that's a chlorine. That's not a hydrogen. Remember, substituents replace hydrogen. Okay? Very simple. Look for the hydrogens. If any of them is not a hydrogen, that's a substituent, and you've got to name it and tell its location. Well, that's a chloro. That's a chloro. Now remember, group 17, those elements change their name from ene, I-N-E, to O. So it's fluoro, chloro, bromo, iodo, if they're on a carbon chain, if they're a substituent. Now, to find out what number the carbon is, you start numbering from the carbon nearest the substituent. Well, the chlorine is right here. So we're going to call that carbon number 1, carbon number 2, carbon number 3, 4, and 5. Okay? That's how we number them, because this is the carbon closest to the substituent. This one right here is the closest. If we numbered it the other way, this would have been carbon 1, 2, 3, 4. So see how the number would have been different? You want the lower number. Now, let me write that down. This will be 2-chloro. What this is saying is that on carbon 2, there is a chloro or a chlorine atom bonded there. That's what it means. Let's put it all together. 2-chloropentane. 2-chloropentane. Notice there's no space here. It's all one word. All one word right there, no space. Notice numbers and letters are separated with a dash. Numbers and letters are separated with a dash. Okay? So that's how we do it. That's kind of a quick little example. I'll do the other one here in a minute. But let's just jot this stuff down, give you a second to write it all down. If you need more time, pause the video. I'm going to take a little sip of my coffee. All right. Now, I'm going to back out of here and come back in. That way that all that work is erased. Now I can start again. Now I'm going to do this one here. Now we're going to work on this one. But again, I'm going to redraw it out here, because I just find it easier to redraw. There we go. Bunch of hydrogens here. You may not find it easier to redraw, and that's okay. You don't have to. This is how I've always done it. I don't know why. I just like working off my own drawings. There we go. Now, let's count carbons. Remember, count the longest continuous carbon chain. So let's start counting. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So notice I counted it numerous ways. I went this way first. 1, 2, 3. So as of right now, my longest chain is 3. 1, 2, 3, 4. Okay, so now I have a 4 carbon chain. So this way, right? That could be it. That's 4 carbons, but let's make sure we have the longest one. The longest one. 1, 2, 3, 4, 5, and 6. So we have a 6 carbon chain. That is most definitely longer than 4. So we're going to name this thing as a hexane. So the longest continuous carbon chain was 6. That's a hexane. So our name is going to be this, that, and the other thing, hexane. That's how the name is going to read. Now, of course, it's going to be more scientific than that. It's going to be not this, that, and the other, but you get the idea. Now, find substituents. Let's circle them in black. There's a CH3 where a hydrogen should have been, and there's another CH3 where a hydrogen should have been. So those are our substituents, here and here. Okay? And both of those are CH3, so both of those are methyl. And we have 2 of them, so write it twice. We'll fix it. I'll show you how to handle this later. But for now, we just want to write down all of our substituents and all of the numbers. Okay? So now we have to number the carbons. 1, 2, 3, 4, 5, and 6. Remember, you start numbering from the carbon nearest the first substituent. Always number from the carbon nearest the first substituent. The first substituent is right there. 1, 2, 3. Okay? 4, 5, 6. And end it. So now, our first substituent is at carbon 2. It's right there. Remember? It's right there. Our second substituent CH, is also CH3, and it's at carbon number 3. So what we're saying here is at carbon 2, there's a methyl instead of a hydrogen. At carbon 3, one of the hydrogens has been replaced and a methyl is there. These are substituents. Now there's 2 of them. Then they're the same. So we have to tell the reader what number the carbons were and what's there. So now here's how you put it together. 2, 3. Numbers are separated via comma. 2, 3. That's how you write it. Numbers are separated with commas. Dash. Now there's 2 of the same substituent, so we have to indicate that in the name. Dash di, because there's 2 of them. Methyl. And it's a hexane. Okay, now let me pull my laser pointer here. 2, 3. So at carbon 2, there's some kind of substituent. At carbon 3, there's some kind of substituent. What is that substituent? Well, dimethyl. So both substituents, 2 and 3, are methyl groups. That's what it's telling me. And the whole thing, the size of the chain, the size of the hydrocarbon, or the alkane, is 6, because it's a hexane. Okay? How's that? I know it's a little weird, but here's one for you to try. Now, yours is written as a skeletal formula. Remember, how to read if you have to redraw it as an expanded, go ahead and redraw it as an expanded. Don't worry about that. Just go ahead and do it. This one's a little tougher because it's a skeletal formula. Don't let that throw you. You're good enough to handle this, I promise. Okay? Use IUPAC rules and name this molecule. It may take you a little time at first, but take the time and learn how to do it. It's not that hard. All right? So I'm going to pause. You pause the video right here. and give this a really good try. I promise you, it's not hard. Remember, start numbering the carbons from the carbon closest to the substituent, the first substituent. Okay? Go ahead and pause the video and give this a try. All right, welcome back. Would you like a hint? Maybe I can help you out. Let me give you a little hint first. Let me number the carbons for you. 1, 2, 3, 4, 5, and 6. So this one's numbered backwards. So if that helps you, pause the video and come on back. All right, welcome back. I think with that little hint, that probably gave it away. I hope it did. So I'm going to redraw it out here like I always do. There we go. Now, I called this number 1, 2, 3, 4, 5, and 6. This is a methyl. That is a methyl. If you don't know that, redraw this thing as a expanded structural formula or a Lewis structure. It'll help you. All right. Now you're all going to hate me when you see the answer. So this has got 6, so it's a hexane, right? It's a hexane. Now we have 2 methyl groups. We have a methyl and a methyl. Looking familiar now, isn't it? We have 1 methyl at carbon number 2. Sorry, not number 1, number 2. And number 3. So this is 2, 3 dash dimethyl hexane. So I gave you the same one, but I gave it to you as a skeletal formula, and I turned it around. That's all I did, though. So I hope you got it. If you didn't get it, please go back and try again. It's really, really not hard. This one's actually a little bit more challenging than normal because I made it a skeletal, and I kind of put number 1 on the right-hand side, which kind of freaks some students out. But you have to be aware carbon 1 could be anywhere. Could be on the left, could be on the right. You have to be prepared for that, okay? So go ahead and try again if you didn't get it. It's not hard. And we'll do lots of practice on this in class, I promise. All right? I hope you're not mad at me. Cis and trans isomers. You've all heard it. You've all heard it. Now, a cis isomer means on the same side or aligned. Okay? Trans means opposite or across. And you've heard these words before. You've heard them when it comes to fatty acids, for example. So let me just draw a double bond. And that's where you find cis and trans. You find them in double bonds. And let me draw the hydrogens in on adjacent carbons, but they have to be part of the double bond. There you go. This double bond is called cis. Let me draw its cousin, or its brother, or its sister, however you want to describe it. This is called trans. Now, the hydrogens have to be on the adjacent carbons, but they have to both be part of the double bond. Okay? So here, carbon number 1 in the double bond, carbon number 2 in the double bond. These carbons are what you have to look at. Okay? These are what you have to look at. Hydrogen here is facing up. Hydrogen here is facing up. So they're both facing the same direction. That's how I know it's cis. You have a double bond, 1 hydrogen on each carbon in the double bond, both facing the same direction. It doesn't have to be up. It just has to be the same direction. Okay? Now let's look at trans. Same thing. We have a hydrogen on 1 carbon of the double bond, a hydrogen on another carbon of the double bond. 1 hydrogen's up, 1 hydrogen's down. They don't have to be up and down. They just have to be opposite of each other. All right, now let's have some fun. It's very simple. I want you to take your hands, and I want you to say to yourself, my hands are hydrogens. Okay? Say to yourself, my hands are hydrogens. And I want you to imagine that your body, your core, is your double bond. So you have a carbon-carbon double bond going across your chest. Okay? Hold one hand in front of you. Hold the other hand in front of you. The relationship of my hands is cis, because they're both going in the same direction. Now, carefully, put one hand behind you. Okay? I have one hand, which is my hydrogen, and another hand behind me, which is hydrogen. Now they're facing opposite directions. This is a trans orientation. Okay? If I put both hands behind me, now I'm cis again because both hands are facing the same direction. If I put both hands back in front of me, this is a cis orientation of my hands. Remember, my hands are my hydrogens. Okay? Trans, cis, cis, trans. And that's how this works. Okay? I hope that exercise was helpful. If not, I just kind of danced a little bit on camera for you. All right, and that's how cis and trans works. So you have to have a double bond. You have to have hydrogens on the double bond. If two hydrogens are facing the same direction, that's cis. They're facing opposite directions, that is trans. So let's take a look at these. Let's look at this one first. Seems like a pretty reasonable one. There's a hydrogen there, and there's a hydrogen there. One hydrogen's facing up, the other one is facing down. So therefore, this is trans. Trans. All right, let's go over to this one over here. One hydrogen on the double bond is here, the other one is there. They're both facing the same direction, more or less at an upward angle. That is cis. Not bad, right? So far, so good. Here we go. Hydrogen here, the double bond. Hydrogen there, the double bond. Oops. Cis. I'm sure you all got that because of my little dancing moves. Probably helped you. Here's one for you guys to try. So go ahead and pause the video. Give this a go. It's not hard. I'm sure you can get it. Come back when you're done. Welcome back. Let's start here. So we have a hydrogen here and a hydrogen there. They're both facing the same direction, so that's cis. Let's try this one. Hydrogen there, both facing the same direction. Cis. Ah, now I gave you a hard one. Oops, sorry guys. Let me get out of here. Go back, there we go. Now we're going to do this one. So let me write the answers in. So cis, cis. This bad boy is hard because I didn't draw the hydrogens in. Now we know they're there. But we didn't draw them in. So that's tougher. That's harder. It's much harder. So what do you do in that case? Well, you look at the carbons instead. So here I have this group here. Here I have that group there. The hydrogens are going to be here and here. So these groups that I've circled, the groups that I've circled are actually opposite of each other, aren't they? So this is trans. That was a hard one. Now, let me just draw skeletal formulas. That's a trans double bond. That's a cis double bond. That's what they look like skeletal formula-wise. So I gave you a hard one, and then I kind of explained it to you. And that's okay if you didn't get that hard one right. Now that you've seen it, I think you can tell that this is trans. And that is cis. If the hydrogens aren't there, they're not drawn in, you can just look at the carbon groups. See how this carbon group is facing up. This carbon group is facing up. This one is facing down. That one's facing up. So you can kind of tell from the carbon groups. It's a little confusing when the hydrogens aren't drawn in, but I think it's pretty easy to tell that these two are different. And I hope that you can, because a lot of times the cis and trans double bonds are drawn skeletal formula-wise. So just get used to looking at them. Not a big deal. And that will be the end of chapter 4. You made it. So I hope that this was a pretty good video for you. I hope that you learned a lot. This is all pretty core fundamental stuff as we're moving forward. So you really need to understand it. So take time, learn it, come to class prepared, and we'll have an assignment and everything will be great. So with that, I wish you good luck and good chemistry.